This is problem number 3 on the sample test problems for test number 1. Discuss the end behavior in both directions of the following functions. Use good limit notation in your answers. In each problem, a, b, c, and d are integers greater than 1. A, f of x equals bx plus cx cubed minus dx to the fifth. So first thing to do is recognize the kind of function this is, and this is a polynomial. And we know that the end behavior of polynomials is dictated by the leading term. That is to say, the term that has the highest power of x in it. And so the leading term in this case is dx to the fifth. But if you actually write that, you're going to get your answers wrong. We need to make sure we include that negative sign. Leading term is actually negative dx to the fifth. Okay, so I'll just draw a few pictures here. If I wanted to draw just y equals x to the fifth, I'm going to kind of think of y equals x cubed because the graphs look quite similar. So I'll just draw x to the third and call it x to the fifth. And the next graph I want to draw is something where it's x to the fifth, but it's negative because of that purple negative sign. So we know that negating a whole function is just going to flip it over the x-axis. So this equation right here could be something like y equals negative x to the fifth. And in fact, that last graph I drew looks like y equals negative anything x to the fifth. So I'm perfectly happy to put a d in there and say, all right, that's the thing that I'm looking for, negative dx to the fifth. So all we have to do now is write down our answers using good limit notation. So the limit of this function is called f of x as x goes to positive infinity. And then we'll go ahead and write down the notation for the other one, and then we'll answer both. So for the first one, x is going to infinity. That means we are running here to the right forever. And as we run to the right forever, we're following this part of the curve, and it goes down forever. So that limit is equal to negative infinity. For the bottom limit, x is going to negative infinity. That means go left forever. And as you do that, you follow this part of the curve, and you see the function goes up forever. So those y values are going up to positive infinity. So here are our two answers to part A. Let's take a look at part B. H of x equals ax cubed minus dx squared over bx cubed plus c. First thing to do is identify the kind of function that we're looking at. This is a rational function because it's a ratio of one polynomial to another. And again, end behavior, so we just need to know the theorem. The theorem here says that the end behavior is determined by the quotient of the leading terms. So what we're going to do is just grab the leading term on top. Highest power of x I see is x cubed, so the leading term is ax cubed. Same thing downstairs, leading term is bx cubed. And I'm just going to divide those two things in the same order they're divided in the original function. So I need this. And you can see that the x's cancel, and I just get a over b. And in fact, I think we're done. We had a theorem that said that if it's a tie, if the degree upstairs is the same as the degree downstairs, then we have a horizontal asymptote. At the quotient of coefficients of those leading terms. So y equals a over b is the horizontal asymptote, which means that if you go at the far left and if you go to the far right, you're going to approach a over b. So if we wanted to use good notation, limit as x goes to infinity of, and this function here is called h of x. So if we go to the far right, this function is going to approach that horizontal line, y equals a over b. And the same thing is true at the far left. So we'll go ahead and put in just one more symbol, plus or minus right there. That's the end behavior in both directions. Both directions approach a over b. Finally, part C. K of x is sine x over x to the a. Okay, I don't really have a good name for this kind of function. It's not a rational function because the top is not a polynomial. It's a trig. So I guess what we're supposed to know here is something about dominance. Here's what I know. No matter what value of x you plug in, sine of x is trapped between the same two numbers. We know that sine x oscillates between -1 and 1 infinitely often as you run to the far right and infinitely often as you run to the far left. The other thing that I want to think about is x to the a. What does this do as x gets really big? So if x is really big and a is some integer bigger than 1, then I think we could say this limit as x goes to infinity is infinity. I can think about y equals x squared. And as x runs to infinity, we follow this part of the graph and we go up to infinity. All right, that's if a is 2. What if a is 3? Y equals x cubed. So it looks like this. And again, x goes to infinity, and again, the y goes to infinity. So I'm feeling pretty good that no matter what power I stick up there, any positive integer, on the right-hand side, it's going to go to infinity. So let's take a look at the left-hand side. Limit as x goes to negative infinity of x to the a. So I'll just look at my two representative graphs again here. Now we're going to send x to negative infinity in both cases. Here, we go up to infinity. Here, we go down to minus infinity. So I don't really have a good way to write that. I guess I'll say something like this. It's infinity if a is a certain kind of number, and it's negative infinity if a is another kind of number. So pause the video if you want to think about this, because we're about to answer it. So I think that we go up to infinity if a is any even power, positive even power, and negative infinity if a is odd. It's actually going to turn out not to matter, because what we've got so far now, we're doing this kind of sine x over x to the a. So what we know is that the bottom is going to go to either infinity or minus infinity. It depends on which direction we're headed and whether a is even or odd. But the top is just bouncing between something between 1 and -1. And so you've got something upstairs, which is relatively small. It's just some number between -1 and 1 bouncing around. But downstairs gets really huge. So this is, very roughly speaking, something pretty small, between 1 and -1, divided by something really, really big. And anytime you have this kind of behavior, the final result actually goes to a nice number. And the nice number is 0. And that nice number depends not on whether the bottom here was going to plus infinity or minus infinity. I can put small over plus or minus huge. It still goes to 0 in the long run, regardless of whether the bottom is positive or negative. So if we have that, then I think we're ready to write down our good limit notation. So this function was called k. So we're going to write limit as x goes to infinity, k of x. And after all that explanation, I think we get 0 for the end behavior at the far right. But we'll go ahead and just abbreviate because in both cases, the answer is 0. So I think I can put a plus or minus here. And on both ends, we get 0 for the end behavior.